Here in chapter 24, we are going to start turning to how light behaves more like a wave than it does a particle. So we'll start off our discussion by talking about something called Huygens Principle. Christian Huygens was a physicist that lived at the same time as Isaac Newton and did a lot of great research on the movement and the properties of waves. And Huygens' principle states that every point on a wavefront acts as if it is a point source. So if you take a wavefront and just divide it into a series of points, each one of those points produces its own tiny little wavelet. And the combined sum of all those wavelets produces the next wavefront. And this is a rather interesting principle, kind of an interesting idea. And yet it turns out that he's exactly right. This is pretty much how it works. We've got a wave that produces tiny wavelets that all combine together to form the next wave front. And that new front produces a bunch more tiny wavelets, which then produce another wave front. How can we show this? Well, one of the easiest ways to show it is with diffraction. We learned a little bit more about diffraction back when we talked about waves at the beginning of the semester. Well, let's talk about it a little bit more here. What happens with diffraction is you have a wave, a straight wave, that is moving along, hits some sort of an obstacle, and of course up here, this wave is completely blocked and it stops. This wave keeps on going straight, but the wave right around the edge of the obstruction bends and starts moving in an outer direction. And why? Why does it do this? Well, that's explained by Huygens' principle. If you have a series of wavelets, a series of points forming waves, then the combined wavelets form the next front. But on the edge, right by the obstruction, there are no other waves to combine, and so that rounded edge just comes from the end of one of the tiny wavelets. And that front produces a series of wavelets as well, which then produces a new rounded edge of the next front. So as a result, you end up with a straight wave that curls around the edge here at some angle theta here. Okay, now that's an obstruction just from half of the wave. What if you have two obstructions? Well, then you have a series of tiny wavelets that add up together. You get a rounded edge on both sides. And if you get the gap narrower and narrower and narrower, your wavelets become smaller or rounder and rounder. And so at the end, where you had just a straight plane wave, you now have a nice round wave coming from a gap. Now there's some really cool things, and we've got subsequent videos that are going to talk about this, where you send light through narrow gaps, and you see that light actually does follow the same principle, and so we know that light is a wave. But anyway, we're going to have a few experiments, including your lab this week, where we send light through narrow gaps and see the effects that happen because of this diffraction. In addition to diffraction, Huygens' principle can also explain the law of refraction. So remember that refraction is where you have a boundary, light comes in, and then when it hits a new medium, the light actually bends and starts moving in a slightly different direction. So what's happening is you have all of these different wavelets as they reach a new medium, but each wavelet has to propagate more slowly in the medium that has a higher index of refraction. And because it moves more slowly, that means that it has to bend into a different direction. think of it this way. So here you have a wave, just like what I drew, but much better than what I drew. And the wave has some certain distance that it crosses, some distance x. But really, it's just the distance between the two wave fronts, and so really, that's nothing more than our wavelength lambda. But it's still just a distance. And we know that velocity is distance over time. So my distance is going to be velocity times time. And so that's another way we can measure it. All right, so here we've got this distance. But as it goes into a new medium, the velocity decreases. We've already seen that. The wave can't move as fast, velocity decreases, and so as a result, your wavelength also decreases. So here, we're going to compare the wavelength of medium 2 to the original wavelength as before light went into it. The wavelength is equal to velocity times time for both, but it's the same amount of time. Interesting point here, and that's critical for looking at this time, t. The frequency of light does not change. So the frequency of light is constant, which means that if you shine a red laser into water, it's still a red laser when it goes into the water. If you shine a green laser, it's still a green laser when it goes into the water. The frequency doesn't change. What does change is the wavelength. Okay, but this time is the same both on top and bottom. And so that gives us the relationship V2 over V1. Well, we saw in the last chapter when we talked about indices of refraction, that V2 over V1 would just equal the inverse ratio of indices of refraction, or N1 over N2. So that means lambda 2 over lambda 1 would equal N1 over N2. All right, let's say that N1 is just air. So we're just going to call that lambda for what it is in air. That's going to be 1 over N2. So the wavelength in water, or whatever medium the light's going into, would be its original wavelength divided by the index of refraction. And that's what is shown right here. So the wavelength in some substance with index of refraction n would equal its wavelength in a vacuum divided by the index of refraction itself. Now, something cool about refraction is that this refraction actually explains mirages that you see, any mirage really. Now, you've probably all seen a mirage. You're driving along the highway, and off in the distance you see a great big huge puddle of water. You drive up, it's bone dry. Well, what happened? That puddle of water you saw was just a reflection of the sky. Here's what's happening. Light's coming from a car, and the forward motion of the car doesn't change. That just moves straight across. And so you actually do see the car. But closer to the ground, it's a little bit hotter. And so the index of refraction changes. Now, since it's hotter, that allows the wave to move a little bit faster. So that causes the wavefront, when instead of being perfectly round, it kind of bends forward like this. As a result, any wave coming down starts to bend forward and moves in this direction. Well, your eye says, well, I saw that light coming from this direction, so I'm tracing it back. That must be where that light actually came from. So your brain interprets that as an image underneath the road. And so you can actually see that in this picture here. There's a reflection of the car in the road. And then you also have the sky, which does the same thing. So you see a reflection of the sky in your picture as well, or in your mirage as well.